Before we get into the instrument, let's lay some groundwork for those that are not totally familiar with the field of dust monitoring and dust control. So the very first question is, what is a dust? According to the U.S. Occupational Safety and Health Administration, popularly known as OSHA, dusts are composed of tiny solid particles carried by an air current, and they can be caused by grinding, crushing, impaction, packaging, and other means. The USA OSHA Dust Control Handbook will provide a guidance for most recent information, equipment, as well as regulations. In addition to OSHA, there is the Mine Safety and Health Administration. This document follows the one written by OSHA, but adds that no chemical or physical changes occur during fracture or grinding or milling operations. A couple of other documents I want to point to include ISO documentation on this subject, but as well the European Agency for Safety and Health at Work. I encourage you to look at these documents since they contain a tremendous amount of information on dust and the requirements and guidances that are required at least by the United States and as well by Europe. Now let's take a look at the sources and examples of the types of dust found in the work environment. One of them is mineral dust. These are those that contain free crystalline silica, such as quartz, coal, cement dust, and the list goes on and on and on. There are metallic dusts, which are composed of lead, cadmium, nickel, and beryllium dust. Each one of these is toxic in its own venue. There are other chemical dusts, which include many bulk chemicals as well as pesticides. We also have to look at organic and vegetable dusts, and these sources are from flour, wood, cotton, and tea dusts. We also have to consider biohazards, and these include materials that are synthesized physiologically active particles. They can also be active or isolated biologically active microbes, or even pharmaceuticals. Then we have the naturally occurring dusts, which include molds, spores, pollens, volcanic ashes, and sandstorms. So the sources of dust are many, and they in our homes as well as the normal work environment. Dust size is generally considered to be less than 75 microns, and this is the reason why that is. Number one, large particles settle more rapidly than small particles, and this depends on the size, the shape, the density, moisture content, air currents, and anything that will allow or propel small particles into the environment or into the atmosphere. Now, just to give you an idea of the differences between these different sizes and how they perform as far as the dust in the environment is concerned, I have a calculation here for spherical particles that have a density of 2 grams per ml. Now what I've done is put together a short chart that shows the size and the settling time based upon that size. Now keep in mind that these are spherical particles, so Stokes' law is really applying here. When we look at a size of 1/10 of a micron or 100 nanometers, the settling time for those particles will be on the order of 315 hours. But as we go to larger and larger sizes, down to 100 microns, we notice that the settling time decreases dramatically. For 100 micron particles, we're looking at a settling time of 4.3 seconds. So these large particles at 100 microns will drop out of the environment very, very rapidly, especially compared to something that's on the order of 100 nanometers. Now, to look at situations that are more realistic, what I've done is provided a sedimentation graph for limestone. Now, limestone has a higher density than the spherical particles we just examined. They have a different shape, and they also have a moisture content that's involved. Now, what I've done is graph this as particle size as a function of sedimentation time in seconds. Now, you notice for a 100 micron particle, the settling time for this particle at this size is only a order of about 0.2 of 1 second. But as we go through smaller and smaller particle sizes, we notice that the sedimentation time is increasing, so that by the time we reach particles that are on the order of 1 micron, the settling time is on the order of 2,000 seconds, or approximately a half an hour. So depending on the material, the settling time will change as a function of the size, the shape, the density, and moisture content. And this has to be examined for each material based upon these various factors. And again, the sources of dust are impaction, abrasion, crushing, grinding, etc. It can also be a source from release of previously generated dust. In other words, we have powder transfer that can occur, and dust is settled within the powder, and during the transfer, dumping, and loading of materials, that dust can be released again. Also, the movement of workers, air drafts, and various actions of machines, such as milling equipment. But another source of dust is that during dust removal, it may not be complete, and as a result, dust resides within the various flat surfaces, the floor, the ceiling, walls, and as a result, vibrations can cause that dust to be released to the environment once again. So there are many types of dust, but these are the 3 newer definitions according to OSHA. The first definition is respirable dust. These are very, very small particles. They penetrate the nose and upper respiratory system, and then finally into the lungs. And also, when these particles are small enough, they can transfer themselves directly across the lung-blood barrier and actually gain access to the blood system. These particles are typically smaller than 10 to 15 microns. Then we move on to inhalable dust, and this is partly a definition by the United States Environmental Protection Agency. These are particles that will be trapped in the nose, the throat, upper respiratory tract, and the median size of these particles is on the order of 10 to 15 microns and larger. Then the third definition is total dust, and this is all airborne particles regardless of their size, anything that can be propelled into the environment, the internal environment or external environment. So with those thoughts in mind, let's think about why is dust control necessary? Well, number one is health hazards. Mineral dust such as silica lead to silicosis. There are metallic dusts that are basically toxic such as lead, beryllium, cadmium, and others. These can lead to illness, impaired vision, chronic illness, or in some cases even death. Flour, wood, tea, molds, spores, volcanic eruptions, pollens, all of these represent well-known health hazards. And when we look at various types of materials such as explosion hazards and fire hazards, these come from wheat storage silos. Years ago, silos were filled with wheat, and the dust from that storage and filling the silo would cause dust to accumulate in various areas of the silo. Then when, in some cases, an electric storm would arise, then the rumbling from the thunder would cause vibrations, releasing the fines and the dust into the wheat silo, into its environment, and then it could catch fire and explode. Then we look at fireworks manufacturing and demolition and explosives manufacture. All these represent hazards on their own, but in the presence of dust, typically below 10 microns, then these materials become very, very dangerous to be around. I recommend that you look at 29 CFR 910 for combustible particulate and how to handle those materials. Dust control also is important to avoiding damage to equipment. Dust can get into computers and digital components. It can get into the general electrical circuitry, and it can also wind up being involved in building up within various types of grinding machines. And as a result, poor product quality can result going forward because in the case of grinding machines, these start to take up places and can cause dulling of the various types of materials used in grinding operations. Also, we have to think about dust and impaired visibility. The danger is that dust can develop on the safety glasses surfaces. And without the safety glasses, obviously, eye irritation can result. Both of these impede person's vision and can cause someone to trip or move in a direction or make a movement that can be dangerous and hazardous to their operations. Also, these dusts can have a certain amount of odors associated with them, and many of these odors could be toxic in their nature. This would impact worker satisfaction as well as morale. Then we have a thought about community relationships. And odors, deposits on homes and cars, and health issues are a constant concern within the community surrounding various operations and manufacturing facilities. And also, as the last thought, it does assure compliance with OSHA as well as the mines and EPA. So there are a number of dust control methods, and I'm not going to go through each of these individually because it would take an awful lot of time. But again, I do recommend those references that I pointed out because they do have information on these different dust control methods. There's settling chambers, baffles, and centrifugal types of equipment that can be used for dust collection. One of the most popular is using filters, and these filters are considered to be called baghouses, and these are very popular in plant environments. These are typically of fabric, and as the dust collects, a higher efficiency results. As the dust collects on the walls of the bag and the fabric, then the smaller particles are captured to a higher degree. There are also wet scrubbers, and typically these are used for air pollution avoidance. And this is typically for industrial particulate and gas streams and water mix. Then there are electrostatic precipitators. These separate particles from exhaust gases, and they use a voltage to attract various charged particles. They're actually this type of device that can be installed in air conditioning and heating systems to remove various types of electrostatic particles, such as pollens and allergens in the home. And again, I encourage you to look at the USA OSHA Dust Control Handbook, since it does provide an excellent source for regulatory information and technical information. Now let's take a look at the Dustmon. And the concept behind the Dustmon is simplicity of design and ease of operation. Number one, it requires a large amount of sample, typically on the order of 15 grams, and you can actually use as much as a couple of 100 grams. The sample is recoverable. Now let's take a look at the instrument, and it's composed of three primary components. One is the optical electronics module. Then there's the powder capture bin. This powder capture bin slides into this place here. Then we have the third, which is the sample holder and delivery. And I'm going to discuss this as an instrument in just a second. Now let's take a look at operating the instrument. The very first step is to transfer the sample, and the sample is held until the start of the measurement within this standpipe. The second step is to enter sample identification. That can be done on this panel meter, or it can be done if the instrument is connected to a PC. The data, if a PC is not used, is displayed on this panel that I'm showing with my cursor. If the PC is used, a much greater amount of data can be accumulated and can be saved for various types of comparisons and other types of data retrieval operations. The third step is to start the measurement. And then the holding valve that's located within this pipe that's holding the sample now opens and drops the sample into the bin. The sample drops into the bin, and the force of the drop causes a dust plume to form within the bin. Then a light illuminates the sample. This light is an LED, and it illuminates the dust plume that is formed as a result of the drop. A certain amount of the light does not pass through the plume, and this reduced light is detected using a silicon detector. Now the data that's obtained, and this is a computer printout, this is from a PC, shows a number of things. The basic graph shows the dust settling curve as it proceeds over a period of time. This is showing the concentration values as a function of time, and this time is given in seconds. So data is extracted, and there are calculations performed that are displayed along this table along here. The other piece of data that can be obtained is the particle size calculation, and this is only for the dust. This is not an indication of the particle size distribution of the actual material. And over here you'll see that the particle sizes, in this case from 45 microns on down, is provided as cumulative percent smaller than data. And in this case it's showing that 100% of the dust is smaller than 25 microns. But very important to us is that 32% of the dust is less than 10 microns, and definitely within the respirable region of the dust sizes. Now what I want to do is, in a second, I'm going to activate this slide. The very first thing that you're going to hear is that there will be a click. That means the valve is opened and the sample will be propelled under gravity down into the bin, and then a dust plume will form. What you can see now is the dust plume that is formed. At the bottom of the bin is the coarser particles that have not been involved with formation of the dust plume. And you can see the light, which again is an LED, it's a white light, that illuminates the particles. And by means of light obscuration, the dust retards the light reaching the detector system that's located over on the left side of the instrument. Now then, let's take a look at actual dust data and start to understand what information we can glean from this data. Now the very first thing, as the dust falls and drops into the bin, there's a very large sharp peak as the initial peak of dust and the accumulation of dust within the bin accumulates and displays itself. Then over a period of time, the dust starts to settle and continues, and with this graph it was taken out to a little bit greater than 30 seconds. This timing can be increased depending on needs, and I'll mention that in just a second. So if the dust does not go to zero, and the 0 point is right along here, within 30 seconds, then there's an indication that the dust is pretty fine and it's going to be persistent in the environment. So one of the things to determine settling time of the dust is to extend this period to 120 seconds or even greater to find out when this dust actually will reach a zero concentration in the plume, and then be an indicator of when the settling has been completed. The dust index value, which is one of the values that are obtained, it's a summation of the very first peak as well as the end value, or what we call the last peak. And this is a good indication of settling over time. This area here where we see this jagged graphic here is an indication of particle tumbling, buoyancy effects, various particle interactions that can occur within the plume itself. Over here, what I'm showing is an example of, and this is a line that I drew for this graph. It shows the sedimentation curve reaching a value of 0. And this happens very, very quick within just a matter of a few seconds. And this indicates that the environment would be very, very clean and dust-free. A couple of the values is the dust area. And for this, we integrate underneath this curve to get an indication of the total amount of dust for comparative purposes. Another value is the dust area plus the max. Now, the max value is located right here. The dust area measurement begins approximately here, and it's an integration underneath this entire curve. Now, with the dust area plus the max, the dust area plus this value allows us to include all the initial conditions as well as the settling conditions. So the combination of dust area plus max provides an indication of overall dust conditions that might be expected from this material. General features of the Dustmon is that its purpose is sedimentation rate, and the size provides a realistic potential for dust accumulation and airborne potential at various production steps. The Dustmon measures powder dust creation potential. It measures dust settling, plus a complete particle size distribution of the dust plume. It avoids air currents, so there was no interference from that type of interference. The valve opening and closing is extremely reliable and leads to high repeatability of these measurements. It's a very simple user interface. It takes on the order of about 5 minutes or less to train someone to use the instrument. Now, the instrument can be used as a standalone system, as I was showing, or it can be operated from a PC that gave the type of data that I've been showing so far. The maintenance is virtually nil. This saves time and it saves money from the expenses of having repairs. High repeatability due to the design of the instrument. It has a sealed sample receiver, which is the bin, and it has a long life light source, which is an LED of 10,000 hours or more. Now let's compare dust for different products, and this is actual customer data, and this basically is an attempt to eliminate subjective judgment as to the dust conditions. This is the entire printout of the data I'm showing blown up below. Now, a couple of things I want to point out is this. Number one, the dust index for this material is 56. The area plus the max that I mentioned just a minute ago gives us a value of 430. This is an indication of high dust. But the customer was expecting no dust. But the value between the area plus the max shows that this is a high dust producer because of the plume that's being formed. Now we take a look at another material, and here the dust index is 46, and the area plus max is 626, which again indicates high dust. The customer also reported that this was very, very dusty. But then we get into another situation, as we did over here with this gray curve, where we experienced a high dust, but the customer wasn't expecting dust. Again, over here with this material, we see a value for the area plus the max, and the value is 340, indicating a moderate dust level. Again, the customer did not expect dust to be present. And the same type of thing can be said with these other types of curves. So there's quite a bit of information and indications about materials and how much dust can be produced, or the expectation. So while visual observations can give an indication of how much dust, the Dustmon provides actual data on the plume and the dust that can form. It also is giving indications out here that, in this case where the blue curve is, that the dust is not settling very well at all, while with the purple curve down here, the dust settles fairly rapidly within about 40 seconds or so. So this would be this material here where the blue curve is would be much more of a hazard than the material giving rise to the purple curve. Then we have another situation that we experienced in our laboratory. We were sent two samples from a customer who had become kind of confused between these two materials. The one material was called coarse and the other was called fine. The experience was that the coarse sample was giving rise to dust that they thought was greater than the fine sample. Well, this is just the opposite of what one would expect, where fine materials would be expected to give higher dust amounts than coarse samples. Our evaluation, according to the Dustmon, showed that the customer was correct in their assessment that the coarse sample was actually giving rise to a greater amount of dust. But in either case, whether it's the fine sample or the coarse sample, the dust was not settling. It's remaining in the environment. And these values here, for these end values out here, 30, 32 seconds, is still very high. So in this case, it would be wise, and I could not continue this graph, it would be wise to make this measurement for 120 or 250 seconds just to monitor how long it would take for this dust to settle. But it still comes back to that question, why is the coarse sample giving rise to more dust than the fine sample? So what we did was some verification testing. At first, we looked at the sample microscopically, and these photomicrographs give an indication of the size of some of these particles. And we first noticed that there's a tremendous amount of agglomeration associated with them. There are some fine particles associated with the sample, but much of it is tied up in these tightly formed agglomerates. The coarse sample, on the other hand, with the larger amount of fines or dust, really is showing a tremendous amount of dust and fine particles compared to the photomicrographs over here for the fine sample. So this was starting to tell us that the Dustmon was doing its job, but we wanted to go a little bit further just to assure ourselves and the customer as to what we were actually seeing. So we ran the samples on our S3500 diffraction instrument. Now this instrument, the way it was set up for this experiment, did not provide any dispersion energy at all. And we tried to maintain these materials in their state as we received them without these agglomerates being affected in any way. So what we found was that the fine sample under this dry powder measurement was actually providing these coarser particles. In addition, the coarse sample showed that the agglomerates, or the coarse particle information, was actually smaller than experienced in the fine sample, but as well there were much greater amount of fines present. And this didn't make sense just based upon the labeling. So what we did was develop a dispersion procedure in water, and the resulting dispersed particle size distribution did in fact show that the fine sample, shown by this magenta, is actually smaller than the coarse sample. So while the fine material would be expected to provide much more dust, it does just the opposite. These particles agglomerated tremendously, and as a result did not form a dust as much as one would expect. So in summary, the Dustmon helps achieve compliance and a safe environment. Dustmon measures the actual dust production. It doesn't measure the entire particle size distribution. Diffraction measures the entire sample and provides the entire particle size distribution, but it does not give any indication as to the actual production of the dust. The dust can have minor inconvenience effects such as sneezing or major deleterious effects leading to chronic illness. Also, this could be a problem with, in some situations, where sick building syndrome is developing. Dust can cause explosions, even in materials such as flour or wheat that one would not expect explosions to occur. The small particle size below 10 microns is a situation that has to be examined because of the propensity of small particles to result in explosions and fires. There are many approaches to removing and containing dust, as I mentioned, and I encourage you to go to those references. And in In the final summary, the Dustmon offers an easy, repeatable, durable instrument to monitor the dust and maintain a safe environment.
Thank you for viewing our on-demand webinar. If you would like to gain better control of your dust, take the first step by submitting samples to Microtrac for evaluation. Simply send an email to the address on the screen to get started. For more information about our entire suite of particle characterization solutions, visit microtrac.com.